Welcome to our lecture on selection on observables. This is the first of a number of lectures on causal inference that will take place as part of core empirical research methods. In past years, these lectures all came together at the end of the term, right in a row. But this year, and in future years, I'm going to try something a little bit different, which is splitting them up throughout the course so that we alternate some programming material and some causal inference material. So this is a lecture that you can work on right after covering linear regression. Let's get started. We're going to be relying on the potential outcomes framework in this lecture and many other lectures on causal inference in this course. I presume that you have at least encountered this before. If you haven't, that's okay, but you might find it helpful to watch the little video that I linked to at the bottom of the slide on potential outcomes, where I go through this quite a bit more slowly. I have another video on selection bias where I also go through it much more slowly, and I write things out using a digital whiteboard as I go. So if you're unfamiliar with these terms, you might want to watch those videos first. That said, I am going to define everything, so it'll be a bit brisk, but here we go. We're going to imagine a scenario where there is some binary treatment, D. So it's either 0 or 1. And 0 will mean you're not treated, and 1 will mean that you are treated. That doesn't have to mean a medical treatment. It can just mean there's some intervention that we're interested in learning the effect of. We want to learn the causal effect of taking some action. And if we do the thing, then D is 1. If we don't, then D is 0. We're going to observe an outcome, Y, and that outcome that we can see is related to two potential outcomes, y0 and y1, via this equation. This is sometimes called the switching equation. Y, the observed outcome, is equal to 1 minus d times y0 plus d times y1. In other words, if d is 0, then y is equal to y0. On the other hand, if d is 1, then y is equal to y1. And another way to write this, which is just a slight algebraic manipulation of the equation I just read out, is to say that the observed outcome y is equal to y0 plus d times the difference y1 minus y0. The fundamental problem of causal inference is that we can only observe one of these two potential outcomes for a given person at a given moment in time. The unobserved potential outcome is a counterfactual, in other words, a what if. So we are imagining that for every person, there is this kind of hypothetical value for the outcome that they would have gotten if their treatment had been different. That's what a counterfactual is. And these potential outcomes are what will allow us to keep track of that idea. It sounds a little strange, but we can make it precise, and we can use it to answer causal questions and understand when we can't answer causal questions with the data we have. We're going to be focusing on this lecture on two different kinds of causal effects. The average treatment effect, or ATE, is defined as the expected value of y1 minus y0, and the treatment on the treated is defined as the expected value of y1 minus y0, given that d is 1. So to make this all a little bit more concrete, let's look at an example. Let's suppose that y is your wage, and d, the treatment, is whether you attend university or not. So if d is 1, then we're saying that you attend university, otherwise you don't. In this example, there are two counterfactuals. If you attend university, so that d is 1, then y0 is the counterfactual wage that you would have earned if you had not, in fact, attended university. On the other hand, if you don't attend university, so d is 0, then y1 is the wage that you would have earned if you had attended. So in this example, the average treatment effect is actually the average effect of forcing a randomly chosen person to attend university. So we're comparing that person's hypothetical wage in the world where she attends, y1, to the world where she does not, y0, to form the causal effect, y1 minus y0, and then we're averaging that causal effect over everyone in the population. The TOT, on the other hand, is the same kind of average with a restriction. So here we are restricting our average to the subset of people who actually did go to university. So we're just pulling out those people who really did go, and then we're comparing their wage y1 if they go to y0 if they don't go. So this TOT is the average effect of attending university for the sort of person who would choose to attend university voluntarily without being compelled. So the big problem that we've got to try to solve is what is called selection bias. And the point here is that we don't, in fact, force randomly chosen people to attend university. So people who do choose to attend are likely to be different in many ways. Now, a question you may have is, why are we so interested in these average treatment effects? Why can't we think about quantiles of the treatment effect? Or what about the variance of the treatment effect? Or what about the share of people who have a positive treatment effect? Well, all of those things are very interesting. In fact, arguably, they're more interesting than the average treatment effect. But we've got a problem. And that problem is called the fundamental problem of causal inference. Namely, we can never observe both y0 and y1 for the same person at the same time. In other words, you either go to university or you don't. So if the outcome here is your wage at age 30, well, we either observe your wage at age 30 in the world where you went to university, in which case we're observing y1, or in the world where you didn't, in which case we're observing y0. We can never observe both of those for the same person. And because we can never observe both of them for the same person at the same time, we can't learn the dependence between those two potential outcomes. So what I mean by that is we couldn't learn their correlation or any other measure of dependence. Because if you think about what we need to measure dependence, we've got to have observations of both of the two things we're trying to learn the dependence between. If I just told you the weights of 20 people, and I told you the heights of 20 people, but I didn't tell you which weight went with which height, then you wouldn't have any way of telling whether weight is positively related to height or negatively. So this is the fundamental problem that we find ourselves in. And what saves the day, well, what partially saves the day, is the linearity of expectation. So this is a very special property. It holds for expectation, but it does not hold for variance. It does not hold for quantiles or other sort of things that you might be interested in. And this property says that the expectation of a difference of two random variables is always equal to the difference of their expectations. And this is completely irrespective of the joint distribution of those two random variables. So it doesn't matter if they're correlated, it doesn't matter if they're uncorrelated, it doesn't matter if they're dependent in some exotic, highly nonlinear way. We can always find the expectation of a difference by taking the difference of the expectations. And this is what makes it possible for us to do meaningful causal inference. It's the reason why average effects are something that we tend to focus on. We can never observe y1 and y0 at the same time, so we can never actually form the within-person difference, y1 minus y0. I can't look at your wage at age 30 with and without university and subtract them to get a number because I only see one of those two. But what I could, in theory, do is observe the y1, in other words, the wage when you do go to university, for a large number of different people. Then I could compute the average of those wages to get the expectation of y1. Similarly, we can imagine, at least, observing the y0, the wage for people who do not go to university, for some large number of people and computing the average of that wage. Now, there's going to be some challenges about exactly whose wages we're going to average when we do this, but conceptually, there's no sort of contradiction in the idea of observing a bunch of y0s, because some people really don't go to university. Similarly, there's no contradiction in observing a bunch of y1s, because some people do. We're observing these different wages for different people, and what the linearity of expectation tells us is that to compute the average causal effect, it's enough to subtract the average of y1 in other words, averaging over one group of people, and the average of y0 averaging over a completely separate group of people. So we replace this infeasible within-person comparison with a feasible between-person comparison. And I should just mention on the previous slide before we skip ahead that if you're interested in learning more about this point, about why we look at average treatment effects, could we look at more interesting objects, you can take a look at Chapter 3 of my lecture notes on treatment effects, where I talk about partial identification, and I look at how it is possible to place some bounds on the joint distribution of the potential outcomes. So I suggested a moment ago that we could compute the wage for a bunch of people who did go to university and for a bunch of people who did not and compare them. Well, conceptually, that's right, but there is another issue that immediately arises. Even though it's not a contradiction to try to do this calculation because it doesn't involve claiming we can observe things we can't, it does run into the problem of what is called selection bias. So suppose that we decided to take the average of the observed wage, y, for a large number of people who went to university. So then we would be approximating the expected value of y given d is 1. Now suppose we did exactly the same thing for a large group of people who did not go. Well, then we'd be approximating the expected value of y given that d equals 0. So what happens if we subtract these two values? This is what I'll call a naive comparison of means, because we're comparing the average wage of people who went to university to those who didn't. Well, we know that if d equals 1, then the observed outcome y is equal to the potential outcome y1. And we know as well that if d equals 0, then the observed outcome y is equal to y0. So this difference of means becomes the expected value of y1 given d is 1 minus the expected value of y0 given d is 0. A little bit of rearranging, and here I'm going to use my favorite trick of adding 0 to an expression. So I'm going to subtract something and add it right back in. That something is the expected value of y0 given that d is 0. When I do that, I'm going to end up with a more complicated expression than I started with, but it's kind of easier to understand. So in the third line of my displayed equation here, I have the TOT. And the way that I got this was by, again, adding and subtracting that expected value of y0 given d is 0, and then by using the linearity of expectation to combine terms. So I combined the two terms that condition on d is 1. So I've got the TOT. Well, that's great because the TOT is a meaningful causal effect. It's a comparison of y0 to y1 for the same group of people, the people who, in fact, chose to go to university. But then there's this leftover term, which we usually call selection bias. This term is a comparison of the mean of y0 for the people who did go to university versus those who did not. And there are sort of two problems that we face here. First, if you were originally interested in the ATE, well, I hate to disappoint you, but the TOT is probably different from it. Because, among other things, you might imagine that the people who choose to go to university do so because they think it benefits them. If that's true, then we might think that the TOT, the treatment effect averaged over people who chose to go to university, is bigger than the ATE. Because remember, the ATE averages over everybody, including those who didn't choose to go. So if we imagine some kind of a model of rational economic agents, or at least people who know somewhat what's good for them, we might expect this TOT to be bigger than the ATE. If so, that's called selection on gains. That's a problem in some sense, but you might say, well, fine, I don't really care about the ATE. I'm willing to settle for the TOT. That might be a perfectly reasonable idea. Well, there's another problem, which is that you've got the selection bias term. So your naive comparison of means is not equal to the TOT. It's equal to the TOT plus something else, and it's very hard to guess exactly what that something else is going to be like. Is it positive? Is it negative? Is it big? Is it small? So what is this something else, the selection bias? Well, It's sort of like a comparison of, if you want to think about it in the education example, it's like the outside option. So it's like the wage you're going to get without going to university. And probably that varies with D. So the selection bias, it would be 0 if the average of Y0 was the same for both the people who do go to university and those who don't. But if people who go to university differ in their outside options from people who don't, then this term is not going to be 0. And we can probably tell a story where that's the case. So maybe people who go to university are on average richer. Well, in fact, they are. Maybe they have had a better secondary school education on average. There might be many ways in which they're different, and those could very plausibly affect their outside option, so the wage they would have earned without going to university relative to the other people in the population. If so, then that selection bias term is not going to be 0, and our idea of doing a naive comparison of means is just going to give us something that's totally uninterpretable, a sum of a treatment effect and some other thing that isn't a treatment effect, namely the selection bias. But by this stage, you may already know there is a solution: randomization. So if we randomly assign the treatment, this problem goes away. If you want to know some more about the details on this slide, you can take a look at Chapter 2 of my lecture notes. You can take a look at a little short video I produced, and also a blog post about some of this material. I have a long blog post about different notions of independence in econometrics. But roughly speaking, we use this shorthand x and this kind of perpendicular sign, but with 2 bars. X is independent of z, is shorthand that we adopt. And this is equivalent to saying that the joint distribution of x and z factorizes into the product of the marginals. So one thing that you need to know about statistical independence that's very important for this lecture and various others, and is also covered in more detail in the notes and my blog post, is that statistical independence implies conditional mean independence. In other words, if x and z are statistically independent, then the conditional mean of x given z is just going to be equal to the unconditional mean of x. And I'm not going to talk you through this integral, but if you are feeling bored, you can take a look and see exactly why that happens. And it just comes from the fact that if the joint distribution factorizes, you can cancel out that f of z. Okay, so under random assignment, what's going to happen? Well, the D, the treatment, is independent of the potential outcomes. It's not going to be the case if you randomly assign people to go to university and not go to university that people who go differ systematically from those who don't. It's going to be random. So if that's the case, then what will happen? Well, the TOT will actually equal the ATE. And here I'm using this statistical independence implies conditional mean independence. So the expected value of y1 given D is 1 will just be exactly the same thing as the unconditional average, the expected value of y1. And the same goes for the expected value of y0 given that D is 1. It'll be just exactly the same thing as the unconditional average, the expected value of y0. And moreover, the expected value of y0 given D is 1 will be the same as when D is 0. If we randomly assigned people to go to university or not go to university, then knowing that you went wouldn't tell me anything about you. In particular, it wouldn't tell me anything about your outside option had you not gone to university. So random assignment actually completely eliminates selection bias, and it also makes the TOT equal to the ATE. Great. It's just kind of problematic in economics because we can't usually randomize things, or at least we often can't randomize things. So here are some great examples of things that we can't randomize. We can't randomize admissions to Oxford, although it would save me an awful lot of time. I would get in trouble. We can't randomly assign how many children a woman is going to have to see the causal effect on labor supply. We can't randomly assign people to watch different news sources and then keep track of who they voted for. It's just not going to work. So the trouble is that sometimes randomization is physically impossible, sometimes it's just impractical, and sometimes it might even be unethical. So I'm not going to randomize some people to smoke 6 packs of cigarettes a day because, well, we know that would be pretty bad for them. Causal inference from observational data is just fundamentally challenging, but it's often the best that we can do. So in this lecture, we're going to talk about one approach to trying to get causal inference from data that did not emerge from a randomized controlled experiment. And here is a simple, concrete example. Let's imagine that there is a disease that is sometimes fatal. The outcome, y, is whether you survive or not. So y equals 1 means you survive. Y equals 0 means that, unfortunately, you perish. Now, what I have done here is, first of all, I have made a list of names, A, B, C, D, E, F, G, H, I, J. And for each of these people, I'm going to tell you whether they were treated or not. So that's the first column, D. I'm going to tell you whether they lived or died. That's Y. And I'm also going to tell you their potential outcomes. So here's the idea. The idea is that there is some dangerous disease and you could die, and then we're going to have a drug, D. And so if D is 1, you take the drug. If D is 0, you don't. Now, what's kind of weird in this table on the slide is that I'm actually showing you all of the potential outcomes. In fact, I'm showing you the counterfactuals. To really drive that point home, I'm putting them in red. The reason that I've done this is because I want to work through an example where we actually know what the right answer is. We actually know what the ATE is. So in reality, you can't see both Y0 and Y1 for the same person. You can't see that Aiden, who did not, in fact, take the drug, D is 0, would have survived either with or without. The only thing you can see about Aiden is Y0. That's why I put that one in black. So the potential outcomes that are in red are the ones that we couldn't really see in real life. But for the moment, what I'd like you to do is use this table to carry out a little exercise. So in some of the past videos, I have asked you to pause and attempt the exercise, and then go check your solutions on the course website. But in this video and in a few of the others, we're going to be working through the exercise in the lecture. So the solution to this exercise is actually going to follow. So it's particularly important in this case, if you want to get the most out of the video, that you pause and ponder. So I'm going to be asking you to calculate 4 things that you can calculate using this full table of potential outcomes. The average treatment effect is number 1. Number 2 is the naive difference of means. Number 3 is the treatment on the treated. And number 4 is the selection bias. If you can't quite remember what those are, go back and rewind the video to find the definitions, then come back to this table, pause the video, and calculate these, either by hand, or if you like, you can calculate them using R. I'm going to use R because this is a bit simpler for me. So here I have some code that sets up a tibble to represent the table from the previous slide. So I've got the names of the people. I'm storing the information about whether they're young or old. We don't need that right now, but we're going to need it later. And then I'm just constructing the Y0, the Y1, the D, and the Y to match the previous slide. And then just towards the bottom of the slide, I'm going to set up my tibble, which I am going to call TBL because I'm not feeling terribly creative today. And then I've got a command here that says RM, which stands for remove. I'm just cleaning up my environment so that if you run all of this code, then you'll end up with only this tibble TBL in the environment and nothing else left over. Well, now that I've got this, I can use the definitions of the ATE, TOT, and so on to compute the objects that I've asked you to compute. So let's first of all talk about this ATE at the top of the slide. So I'm using dplyr. So I'm going to pipe this tibble into the summarize verb. And what I'm going to summarize here is mean y1 minus y0. That's exactly what the ATE is. What the pull command does here, if you remember that from one of our earlier lectures, is that it actually it takes the tibble that would otherwise be returned by the summarize command, and it converts it to just an ordinary vector of length 1. So basically the point here is that dplyr commands always return a tibble. If you want what you're returning to not be a tibble, you can use pull. Traditionally, you would use pull to get, say, like a column, to get a column out of a tibble as a vector. Here I'm using it to get a scalar out, which, because R doesn't actually have scalars, is just a vector of length 1. So I'm not going to comment on that pull when I encounter it elsewhere. So that's how we compute the TOT. How would we, rather the ATE, how would we compute the TOT? Well, it's the same thing, but now we're just doing the averaging over the people who were really treated. So I'm going to use exactly the same steps as above for the ATE, only now I'm going to filter only those rows for which D is equal to 1. All right, that one's also fairly straightforward. How about the selection bias, which I will abbreviate by SB? Well, this one is a little bit more complicated. Maybe you used a different approach, but here's what I did. I used a group by command. So I formed groups based on the treatment status. So D is whether you took the drug or not. And then what I've done is I've actually computed the mean of Y0. So when the first two steps of this pipeline are finished, what I'm going to have is I'm actually going to have two columns. In the first column, I'm going to have D, 0 and 1. And in the second, I'm going to have the corresponding mean of Y0 for that group. So I'll have the Y0 mean for the untreated and for the treated. Then I'm using pull to grab just the column Y0 mean. Then I'm using diff to take the difference between the two elements. Wow, there's more. Well, we can also compute the mean of Y when D is 1 and the mean of Y when D is 0, which I'm doing here with another group by command. And here I've actually displayed what the output's going to look like. And then I can use this same strategy with pull and diff to compute the naive difference of means. Okay, so here is a nice clean summary of everything that we've done so far. So in my example, the ATE was 0.2, the naive difference of means was 0, the TOT was 0.25, and the selection bias was minus 0.25. And you may notice, you remember from our decomposition a few slides back, that the naive difference of means has to be equal to the TOT plus the selection bias, and indeed, that's exactly what we get here. So we can do a sanity check, and everything works out. So what's going on in this example? Well, if you go back to the table, what you will see is that I have induced selection into treatment. The people who are treated, in this case, the people who take the drug, are on average older. Okay, well, we're going to need to try to do something about that. But before we do, let's linger for a moment on this column X that we haven't talked about so far. So I just mentioned that there are young and old, and I've tried to choose some names here that will suggest different eras of history. So the conditional average treatment effect is an average treatment effect when I condition on some observed characteristic. So we usually abbreviate it CATE, C-A-T-E, and CATE of little x is defined to be the average of y1 minus y0, conditional on x, which is some set of observed characteristics, taking on the value little x. So using this definition, I would now like you to, again, pause the video and take a moment to compute the conditional average treatment effect for the young, the conditional average treatment effect for the old, and then I would like you to tell me how these relate to the overall average treatment effect. So take a moment, pause the video, try this out, and then I will show you my solution. All right, well, we can do this with dplyr. It's pretty straightforward. We're again going to use a group by, and I'm going to summarize CATE equals mean of y1 minus y0. I hope by now you're getting the hang of these of these steps. So what do I end up with? Well, I'm going to end up with 2 different ATEs, one for each group. So for the old, there is a positive conditional average treatment effect. It's a third. Whereas for the young, there is no treatment effect. So I've created a scenario where we've got a drug that doesn't do anything for the young people, but actually helps the old people, makes them much more likely to survive. All right, so what we are now going to do is we're going to take a look here at the relationship between the overall average treatment effect and the conditional average treatment effects for the old and the young. So how are we going to do this? This is a slightly more complicated set of steps. So I'm still going to group by x, which was the age variable, and I'm still going to compute the conditional average treatment effect, just as before. But now I'm also going to construct a count. So to count the number of observations in a group when you're using dplyr, you can rely upon the function n. So n with parentheses is just going to return the number of observations in that group when it's used within a summarized verb statement that follows a group by. So as you can see, what's happening here is it's an extension of the calculation we did on the previous slide. So we've still got the conditional average treatment effect for each value of x, where x can be young or old. But we've also got a count, so we know how many people are in that group. And then finally, I have computed, using a mutate statement, p of x. So this is the share of people with that value of x. So that's just the count divided by the sum of both of the counts. So 0.6, or rather 60% of the people in my little example are old and 40% are young. And you may have heard of the law of iterated expectations before. I sure hope you have. Next to the linearity of expectations, it's probably my favorite fact in all of probability because it's very, very useful. So we can use the law of iterated expectations as follows. So we can take that group stats tibble from before, and then we can simply multiply the conditional average treatment effects by the share of people in that group and sum them. When we do that, what we should get is exactly the same thing as the ATE, because the ATE is just the expectation of the conditional average treatment effect. So we plug in each of the values of x, and we weight by the share of people with that value of x. Does it work? Well, it had better work. It's the law, and indeed it does. So we get the same value in each case, which is 0.2. All right, so by now maybe you're wondering, where are we going with all of this? Aren't we supposed to be trying to do causal inference? All you've been doing is giving me potential outcomes I'm not going to have in real life, and then having me compute things that, of course, I couldn't compute without observing those unobserved potential outcomes. All right, well, we're now going to return to reality and actually consider what happens in the real world, which is where we cannot observe those red potential outcomes. But before we do that, I want to just review what we've seen so far in this example. First of all, in the disease example, there is selection into treatment. So the old are more likely to be taking this drug. So you can see that among the people who take the drug, we've got Dakota, Herbert, Irma, and Julius. Well, only Dakota is young. The rest are old. But it's also the case that the old, well, they have systematically different potential outcomes than the young. So you can see that the young are much more likely to survive without the drug. So the Y0s of the young tend to be 1. In fact, they are all 1. That's why there's no treatment effect for the young, because their Y0 equals their Y1. Whereas for the old, that's not the case. So at least for Ethel and Herbert, if they take the drug, they're going to survive. So we've seen that the naive comparison of means does not give us the ATE because of this selection into treatment. We've seen that iterated expectations shows us that if we knew the conditional average treatment effects, then we could always average them to get the ATE. So here's the idea. The idea is maybe if we adjust for age, maybe if we somehow account for age, then we can address this selection problem. And the title of this lecture is Selection on Observables. This is, in fact, a pair of assumptions, and it's a pair of assumptions that shows us when this particular idea, the one that I just mentioned about adjusting for age, is going to work out and actually solve our causal inference problem. I'm going to introduce a little bit more, I'm going to introduce a little bit more notation and terminology now. So I said a moment ago that the old were more likely to be treated. We would like to see exactly how much more likely they are to be treated, and we'd like to do that using the propensity score. So the propensity score is defined as the probability of being treated given your observed characteristics X. So in this case, it's going to be the share treated by age group. So I'd like you to compute the propensity score for the young and for the old. This should be a quick exercise. All right, so if we take a look here, we can see that conditional on being young. So let's take a look at the people who are young. They're at the top of the table: Aiden, Bella, Caden, and Dakota. Well, conditional on being young, you have a 1/4 chance of being treated because only Dakota is treated. If we look at the bottom of the table, Ethel, Floyd, Gladys, Herbert, Irma, and Julius, well, how many of these folks are treated? 3. And how many of them are there? 6. So the propensity score is 1/2. Old people are more likely to take treatment, and they're also more likely to die with or without the treatment. So we would say that age confounds the relationship between D and Y. So here's some wishful thinking. The wishful thinking is, wouldn't it be great if somehow within age groups there were no selection problem? Because if that were the case, we could learn the conditional average treatment effect for each group. So when I say, wouldn't it be great if within age groups there were no selection problem, what I'm saying is, wouldn't it be great if the naive comparison of means, the one that we know doesn't work, actually did work when you restrict attention to a certain age group? So if we looked only at the old, so X equals old, and we compared the average outcome of the treated to the untreated, wouldn't it be great if that actually gave us the conditional average treatment effect? Similarly, wouldn't it be great if when we conditioned on being young, so we restricted attention to Aiden, Bella, Caden, and Dakota, and we then took the naive difference of means, treated minus untreated, conditional on young, it would just be amazing, wouldn't it, if that actually somehow, just by chance, happened to give us the conditional average treatment effect for the young? Well, you've still got the potential outcomes. I haven't taken them away from you yet. So why don't you calculate and see whether, in fact, in this example, my wishful thinking turns out to be more than a wish, but actually correct. Well, perhaps it wasn't a surprise given how much lead up there has been to this slide, but it works. It works in this example, and I cooked it up so that it would work. So there are 2 blocks of our code here, one to the left, one to the right. Okay, so let's take a look here. What's going on in this one to the left? Well, in the one to the left, I am computing the conditional average treatment effect for the old and the young. So on the left-hand side, I am using those potential outcomes y1 and y0. So if you want to think about it this way, the left-hand block of code on this slide is something that you definitely could not do in real life. In real life, you could never observe y1 and y0. You can only observe one or the other for each person. So this is a completely infeasible comparison, but we've made a little example where we pretend that we can see all the potential outcomes, and we can see them for the whole population of people, 10 people in my population. So that's the right answer. That's the truth on the left-hand side of the slide. The old have a Kate of 1/3, and the young have a Kate of 0. On the right-hand side of the slide, we are finally in the realm of reality, where we're going to be computing things that we could actually see in real data. So on the right-hand side of the slide, I'm using a group by command now with 2 arguments. I'm going to group by X, which is the age group, and by D, treatment status. So I'm now going to compute the average outcome. I'm going to compute the average outcome for each combination of age and treatment status. So you can see that untreated old people have an average observed outcome of 0. Treated old people have an average observed outcome of a third. Treated young people have an observed outcome of 1, and so do untreated young people. So now, again, my idea was that maybe we're going to get lucky, and maybe the conditional average treatment effect is the same thing as the naive comparison of means within a group. So let's try this out. Let's look at the old. If I just take the naive comparison of means, D is 1 minus D is 0 for the old, I'm looking at the numbers in the right-hand table, I've got 0.33 minus 0. Okay, so does that match what we've got in the left-hand table? Well, yes, it does. So indeed, the old now in the left-hand table have a CATE of 0.33. So let's go back to the right-hand table. Let's try this naive comparison of means for the young, the treated minus the untreated. Well, for the treated, their mean y is 1, their mean observed outcome. And for the untreated, their mean observed outcome is also 1. 1 minus 1 is 0. So let's go check back on the left-hand side table. Is the CATE equal to 0? Yep, it works. So now we've got the conditional average treatment effect for each group, and we did it using things we can really observe in the real data. Everything in that right-hand side table depends on y, d, and x. Those are all observed things. We can observe the observed outcome. That's why we call it the observed outcome. We can observe the treatment. And I'm stipulating that we can observe whether these folks are young or old. So that's an assumption that we've got this age information at our disposal. And now that we've found a way to compute the conditional average treatment effect for each group, again, we can just use the share of young and old in our population to average those conditional ATEs to get the unconditional ATE. This is just an application of the law of iterated expectations, and it's the same exact one that we looked at a few slides back. So it worked. Why did it work? Well, it worked because some assumptions were satisfied. Some assumptions that I am now going to flesh out for you. So we talked a few slides back about the notion of independence, statistical independence. We're now going to introduce a related concept, namely conditional independence. So the way that we express conditional independence is we use the same symbol as before, except with a conditioning bar. So W, that funny perpendicular looking thing, Z, and then a bar, R, we would say W is independent of Z, conditional on R. And what this means probabilistically is it means the joint distribution of W and Z given R factorizes into the product of the marginal distribution of W given R times the marginal of Z given R. So this is exactly the same idea as for independence. The only thing that's different is we've got conditioning on R everywhere. And if you would like more details on this, you can take a look at Chapter 2 of my lecture notes on treatment effects. And I've also got a video that goes into this in some more detail. It's a short video that you can watch by clicking on the link. All right, so here are the two selection on observables assumptions. The first assumption is called selection on observables. Basically, this says that D is independent of the potential outcomes given X. And I should say that we could weaken this to conditional mean independence. That's actually all we're going to need. But you'll often, and perhaps most commonly, see it stated as an independence assumption. So what does this imply? Well, it implies that people with the same observed characteristics have the same potential outcomes on average, regardless of whether they were actually treated or not. So this is exactly what we relied upon in the example with the old and the young a moment ago. So we said that after adjusting for age, we had the same potential outcomes on average, regardless of whether someone was treated or untreated. That's why we could do a naive comparison of means, treated minus untreated, within age group. So this assumption can sometimes lead to a bit of confusion. And I have a blog post that talks about some common confusions that I have seen students have about this assumption. So if you'd like to go and take a look at that, it might help you to understand what this assumption says, and also, perhaps more importantly, what it does not say. The first assumption was selection on observables. The second is overlap. So this assumption says that the propensity score, as a function of the characteristics x, lies strictly between 0 and 1 for every possible value of x. Let's just remember what the propensity score is. The propensity score is the probability that you are treated given all the stuff that I can observe about you. In our little example, the stuff that I could observe was just whether you were young or old, but in another example, that could be lots of other information. So what does this say in words? Well, what it says is among people with a given set of characteristics, x, some, but not all, are treated. So for example, it says some old people are treated, but not all. And some young people are treated, but not all. In a more complicated example, it would be something like, after I form a group based on demographics and age and state of birth, I'm going to have a group of people. In that group of people, some get the treatment and some don't. Now, the reason that we need this, it might be obvious, it might not, but if you think about it for a moment, is that we're going to try to compare within group, among people with a certain set of characteristics, we're going to try to compare those who got the treatment to those who didn't. But if everyone in that group was treated, we can't make the comparison. Similarly, if nobody in that group was treated, we also can't make the comparison. So this overlap assumption is what we need to make sure there really are some people to compare to after we've drilled down to these groups that are defined by the characteristics we can observe, x. All right, so now we've actually already done regression adjustment. We just haven't used that term. So in the slide, a few slides back, I should say, what we did was we formed strata based on a common value of the covariates. Within each stratum, we computed the average outcome among treated and untreated. Then we subtracted these to estimate the CATE, which is a stratum-specific ATE. Finally, we averaged the stratum-specific ATEs, weighting by the fraction of people in each. So that's called regression adjustment, and here is the main result. Under the selection on observables and overlap assumptions, so assuming those hold, the conditional average treatment effect is equal to the naive comparison of means, treated minus untreated, for people with that particular value of x. And then, of course, by iterated expectations, we can use this to learn the ATE. I am not going to do the proof in this particular recording, but if you would like to see it, you can click on the link here to see a kind of a pen cast where I work through the proof. You can also go to the course website and pull up these lecture slides, and I have reproduced the key ideas from that proof in the appendix to these slides. I do recommend, by the way, that you take a peek at that proof, but it's not necessarily crucial for understanding what's going to happen next, so you can view that later at your leisure, and feel free now just to keep watching and see what comes next. Okay, it's called regression adjustment, but can we actually implement it with a regression? Well, you're going to think about this in one of your problem set questions, but I want to help you get started. So let's look at a little example now. It's actually going to be the same one we've just looked at. Let's suppose that, just for the sake of argument, keep life simple, all the covariates were binary. So they could be things like age, young, old. They could be things like other sorts of categories that people could belong to. So just imagine a large number of these dummy variables. Their x are all binary. So let's take these covariates. Let's center them around their means. So I'm going to take the vector x and subtract x bar. I'll call that thing x tilde. Now, suppose that I regress y on d and x tilde and all the interactions between d and x tilde. Okay, well, then the coefficient on d is the ATE, and its standard error is correct. That's going to give you the correct standard error for the ATE. So let's take a look on the code here on the slide. How can I do this? Well, I'm going to pull out the variables old and x tilde. So I'm going to construct a dummy variable. X is going to be 1 if someone is old. I should say, let me correct that. X is young or old. But in this mutate statement, I'm going to construct a dummy called old that takes on the value 1 if x is equal to the string old. Then I'm going to construct x tilde, which is going to be old minus mean of old. So now I am able to run my regression. So a very easy way to run a regression that includes two variables and their interaction is by using this asterisk. So y tilde d asterisk x tilde runs the regression of y on d, x tilde, the product of d and x tilde, and an intercept. And here I'm using a pipe to send the data into the mutate and then into the regression command. So in order to supply the data as the second argument to the function lm, I need to use this underscore. So I say data equals underscore, and that changes the behavior of the pipe so that rather than piping in the first argument of the function lm, it's piping into the second argument. And then I'm just going to clean this up to make it look a little bit easier to see. And now we get the causal effect. So the coefficient on d is what we want. We get the estimate and standard error. So I should just add one tiny, teensy little caveat. When I said the standard error is correct, there is a slight subtlety there. And the subtlety is that I have not adjusted for sampling variability in x bar. Now, whether that's a problem or not actually depends on your perspective. It depends on what it is that you're after. That's not crucial for this lecture or this course, but if you would like to know some more, and if you'd like to see much more detail on exactly how regression adjustment works and why running this particular regression does the trick, I've written a rather lengthy blog post. You can click on the link at the bottom of the slide. And this blog post, of course, is optional, but you may find it quite helpful for one of your problem set questions. That's regression adjustment. But it's not the only approach. Another approach that, in theory at least, should take us to exactly the same answer, in other words, assuming that the assumptions hold, is called propensity score weighting. And now this one is a little bit harder to wrap your head around for most people, so let me try to give you a bit of intuition here. In the disease example, older people were more likely to be treated and also more likely to perish regardless of whether they got the drug or not. So you can think about this as saying, well, there are too few young people among the treated. The people who got the drug were mainly old people. The flip side of this, of course, is that there are too few old people among the untreated. So in each case, what I mean when I say too few or too many is relative to what we would have in a randomized experiment, because a randomized experiment is on average going to balance any characteristic, like age, across the treatment and control groups. Well, how could we fix this? Well, one idea is to actually upweight treated young people. So to give them extra weight when we're computing the average outcomes for the treated and untreated groups. All right, so how could we do this? Well, here is the main result. This is not the proof. This is just the result of doing the proof. So it turns out that the average treatment effect is equal to, the expected value of this particular weighted average of y, w1 of x times y, minus the expected value of w0 of x times y. And what are these w1 and w0? Well, there's some weights, and here's how they're defined. So w1 is d, that's the treatment indicator, divided by the propensity score function, so the propensity score of x. And w0 is, in some sense, it's like the complement. It's not exactly the complement. It's the numerator and denominator of w0 are the complements of the numerator and denominator of w1. So in place of d, we have 1 minus d, and in place of propensity score, we have 1 minus propensity score. And it may be kind of hard to see why this works, but if you think about it, you look at d over p of x, well, when does that thing actually have a big value? Well, when p of x is really small, right, so the denominator is small, that thing gets blown up. It becomes very large. But when d is 0, it doesn't have any effect at all. So if you think about how the weighting works, this W1 function is going to take a person who is treated, d is 1, but who belongs to a group that has a very low share of treated people, propensity score is small, and give that person extra weight. Similarly, if we look at W0, what's happening there? Well, the numerator is 1 minus d. So this weight is going to be equal to 0 if a person is in fact treated, and it's only going to be positive when that person is untreated. So what happens with this W0? This is taking people who were not treated, and it's giving them weights that, again, relate to how likely they were to be treated. But if you think about how this differs from W1, again, the complement means that if p of x is small, so if you belong to a group where very, very few people are treated, well then 1 minus p of x is actually bigger. So when is 1 minus p of x small? Well, that's when p of x is big. So W0 is going to give a lot of weight to people who were not treated but belonged to a group where most people were treated. So although it might not be completely obvious why this is the precise form the weight should take, at least the story that I'm telling as I explain the meaning of all the terms in those weights does seem to align with the intuition from the slide. So it is going to upweight treated young people and untreated old people when computing the averages. I should just mention that there is a proof of this theorem, and you can find that proof by watching this additional short video. You can also go to the appendix to these slides, which you can view on the course website. So let's actually do the calculation, because I have found that with propensity score weighting, people find it much more concrete if they actually do it using some real numbers. So what I'm going to do is I'm going to form this tibble, which I'll call PSW, which stands for propensity score weighting. First, I'm going to group by x. Remember what x is. X is the observed characteristics. So in our example, it's just age. It's either young or old. Then I'm going to compute the propensity score, which I'll call p-score. So that's the probability of being treated, conditional on x. So I've already grouped by x. So I'm now computing the mean of the treatment indicator, and that's exactly the same thing as computing the share of treated people in each group. Now I'm going to use an ungroup command. If you haven't seen the ungroup command, what it does is it tells dplyr, hey, you know how a moment ago you were doing some calculations by group? I want you to stop doing that. So I want you to now return to using ungrouped calculations. Okay, so now what I'm going to do is I'm going to use a mutate statement. So I'm going to calculate these weights. Now you might be wondering, well, hang on, group by, mutate. Usually what we've done in the past is we've used group by with summarize. Here you're using it with mutate. What's going to happen? Well, you'll see in a moment, I think, if memory serves about what's on the next slide, but what I'll say is this. Summarize reduces the size of a tibble. So if you do a group by followed by a summarize, then you're only going to have as many rows as you have groups. If you do a mutate instead, then what's going to happen is that dplyr will actually pad out the values to make sure that you have exactly as many rows as you started with. So not as many rows as there are groups, but as many rows as there were rows in the original tibble. So in this case, what that means is that the propensity scores for the old people are going to be repeated, so that every single old person is going to have that propensity score attached to them. And this is, in a moment, as we'll see, exactly what we need, exactly what we want. And that is because, after our ungroup statement, now we're back to plain old ordinary dplyr mode, not grouped. Now we're computing the weights. And the weights will vary across the individuals, but there's a common component. So for people with the same value of x, they have the same propensity score, but they might not have the same weight because the weight depends on their D. So we're going to form weight 1 and weight 0. Everybody has a weight 1. Everybody has a weight 0. But if you are treated, I should say if you are untreated, your weight 1 is just 0 regardless of what your propensity score is. And if you are, did I say that backwards? If you are, I hope I didn't say that backwards. Let me try one more time. If you are untreated, your weight 1 is just going to be 0. If you are treated, your weight 0 is just going to be 0. But other than that, these weights are going to take on some value that depends on the propensity score. So since everybody is either treated or untreated, it means that everybody is going to have a positive weight for one, but not the other of these two columns. And fortunately, my prediction was accurate, and I did actually print out the whole table of values. So now you can see what we got. For every single person, we've got the propensity score, which is the share of people in their group who are treated. So that is a function of age. And we've computed the weights. So you can see Aiden, Bella, Carter, Dakota. Well, let's take a look at Aiden, Bella, and Carter. Aiden, Bella, and Carter were not treated. So their weight 1 is just 0. Dakota was treated. She is that extremely rare example of a young person who actually got the disease. Actually got the drug. So we need to give Dakota extra weight. And what our propensity score weighting says to do is actually to give Dakota a weight of 4. Now, if you think about that, that actually makes perfect sense. If Dakota is the only young person who got the drug, then she's got to somehow stand in for all of the young people. So this weight 1, if you look at the weight 1 among the young, is actually summing up to the number of young people, 4. Similarly, we can look down here to the we can look over to the weight 0 for the young, and what do we get there? Well, 1.33, 1.33, 1.33, and 0 for Aiden, Bella, Carter, and Dakota. Again, they sum to 4. They sum to the number of young people, number of people in that particular group. So why are they 1.33? Well, Aiden is untreated, so that means that her weight 0 is actually going to be just equal to 1 over 1 minus the propensity score. And that's exactly what 1.33 is. It's the same for Aiden, Bella, and Carter. We can go through the table for Ethel, Floyd, Gladys, Herbert, Irma, and Julius. And what we're going to see again is that these weights sum up to the number of people in the group. So we really are upweighting the young people who got the drug, and we are in some sense sort of downweighting the old people, or rather we're upweighting the old people who did not get the drug. Okay, so now we can use the propensity score weighting equation to figure out what the ATE will be. So what are we going to do here? First of all, I'm just going to show you that the weights, the sum of weight 1 and the sum of weight 0, actually add up to the total number of observations. So why does that work? Well, it's something that you could kind of work out algebraically, but you could also see it in the example on the previous slide, where indeed these actually summed up to the total number of individuals in the population. And now we can carry out the propensity score weighting. So what do? We're going to summarize. So we're going to compute a summary statistic based on this PSW tibble. The weight times the y. So we have the weight 1 times y. We're going to compute the mean of that, minus the mean of weight 0 times y. And indeed, we get 0.2, which is exactly the ATE, and exactly what we claimed that we would get. So it does work. We're drawing near to the end of this lecture, so it's time to reflect a bit on what we've done. So we have a couple of assumptions, and we have used them and shown that if those assumptions hold, then we have 2 different ways that we could try to carry out causal inference from observational data. We could either use propensity score weighting or regression adjustment, provided that this overlap assumption holds and the selection on observables assumption holds. So you might be wondering, it's a good question, can we evaluate these assumptions? Well, with overlap, the answer is yes. So because we can observe both d and x, then we can check this directly. So the more characteristics we put into x, overlap actually gets harder to satisfy. If you think about this, the smaller and smaller I make my group, if I add more and more and more and more conditions, then the more likely it is that I'll eventually get a group that's so small that there are only treated people or only untreated people in my group. So more characteristics in X makes it harder to satisfy overlap. Fewer characteristics makes it easier. And we can just check this because we can observe the D and the X. Well, what about the selection on observables assumption? Unfortunately, without some access to outside data or additional assumptions, there's just no way to check this assumption, and that's because it's about unobservable things, namely the potential outcomes. All else equal, the more characteristics we put into X, the more plausible selection on observables becomes. Think about it another way. Selection on observables says that the selection the selection into treatment is governed by some X's that we can see. Well, what's the risk here? The risk is just not including enough X's, in the sense that maybe people's decisions depend on all kinds of things, and if you could just observe all those things and condition on them, you'd be fine. So the risk on this view is leaving out some of those characteristics. So in some sense, the overlap and the selection on observables, they're opposite in the way that they work. One can be checked using the observed data, the other can't. One gets harder to satisfy when there are more covariates. The other, in some sense, becomes more plausible when there are more covariates. I should, however, sound a note of caution about this claim that more X's makes selection on observables more plausible. More is not always better. There is something called a bad control, and we have a whole lecture about that coming up. There are some kinds of characteristics that definitely should not go into X, and we will definitely say more about that soon. Another point that we might want to raise is, are we even really interested in the average treatment effect after all? At the beginning of the talk, I should say the beginning of the lecture, I sort of said, well, we might or we might not be, and I mentioned this thing called the TOT. The ATE, if you recall, is the average effect of forcing a random person to be treated. But of course, in real life, in social science settings, we usually can't force someone to be treated. We can only offer treatment. The TOT, on the other hand, is the average benefit of treatment for people who will voluntarily take it. Or another angle on this is that it's the foregone benefit, the benefit you lose, per person if you discontinued a program. So maybe we don't actually want the ATE. It really depends on our perspective. The ATE might be relevant if you were deciding for yourself whether you wanted to take a drug, because you can, in some sense, compel yourself to take an action. And then you're saying, well, if I view myself as just one randomly chosen person from the population, then maybe the ATE is the relevant causal effect for me. But if we, on the other hand, are policymakers, and we're thinking about bringing in a program that will be voluntary, or on the other hand, canceling a program that already exists and is voluntary, then actually the TOT might be the more interesting object. So maybe we don't want maybe we don't want the ATE, but also maybe we can't get the ATE. So most models of rational choice assume that agents compare the costs and the benefit of the choices they're making. So the benefit of treatment is related to, or perhaps equal to, but perhaps let's be a little bit more circumspect and say related to, y1 minus y0. And selection on observables would imply that the expectation of y1 minus y0 given d and x doesn't depend on d. In other words, it would say that the average treatment effect, once you know x, telling me the value of d, telling me whether someone really chose the treatment or not, doesn't tell me any additional information. So what does that mean? Well, that means that economic agents either lack or don't act on private information about the gains from treatment. So another way of putting that is that assumption, that selection on observables assumption, says the agents don't know anything that we don't know that's relevant for their treatment effect. And that might actually be a very, very strong and highly implausible assumption in some settings. So, fortunately, there's actually a way to do this selection on observable stuff with the TOT. And we can do it using a weaker assumption. So here I'm going to describe how to do this for regression adjustment. There's also a version for propensity score weighting. So here are the assumptions. The assumptions are weaker. So now, instead of the selection on observables assumption, which said that it said the conditional on X, there's no relationship between the potential outcomes and D. Here we're only using that for Y0. So we have no assumption about how Y1 is dependent on anything. So what we're saying here is, on average, if I know your treatment and your covariates X, then anything that I want to say about the average value of your Y0, I could have said that with only X alone. So knowing that you were treated or not doesn't tell me anything extra about your Y0 on average if I already know your X. Similarly, we can weaken the selection on, we can weaken the overlap assumption. So now overlap just says that the propensity score is strictly less than 1. It's allowed to be 0. So notice that these two assumptions place absolutely no restriction whatsoever on the relationship between the treatment effects and D. It's perfectly fine if people are selecting into treatment based on unobserved information, unobserved to us, the econometricians, about their private treatment effects. That's completely fine. And the overlap condition is also weaker. It's perfectly fine if for some values of X, there are no treated people. So we have a theorem here which says that we can use these assumptions to learn the TOT. How do we learn it? Well, we just take the average of Y among the treated, and then we subtract this conditional average of this is actually slightly complex. Let me tell you what this says. This says that I take the mean of Y given that D is 0, conditional on X, and then I average that over the distribution of the covariates X among the treated. So I'm taking an average of this mean of Y given D is 0, X, but I'm plugging into it the distribution of X in the treated subpopulation. So I'm taking an object I computed for people who were not treated, conditional on X, and then I'm reweighting it using weights that correspond to the X's for people who actually did get the treatment. So that is the end of this lecture on selection on observables. As I mentioned, there is an appendix, and you can go to the course website to download the slide deck, and you can see the appendix slides. I'll just show you that these contain a derivation of the regression adjustment formula, also the propensity score derivation, and finally, they contain this argument for the TOT via regression adjustment.